Hello to all. Yesterday we had part 1 of the topic atoms, molecules, mole concept. Now its part 2. We will try to interrelate atoms, atomic weights, molecules, molecular weights, and number of moles to each other. The concept of mole, which started with atomic weight expressed in grams, molecular weight expressed in grams, and its interrelation we discussed in the last lecture. I will give just a few examples before we proceed further. We have this is nitrogen. Its atomic weight is 14 AMU. Its atomic weight is 14 AMU. We shall write 1 mole of N equivalent to 14 grams equivalent to 6.02 10 raised to the power 23 what? Atoms or molecules? Atoms, because this is in the atomic state in atom. If we had N2, it is a molecule. We shall write its molecular weight 14 into 2, 28 AMU. What's the relation? 1 mole of N2, 28 grams, 6.02 10 raised to the power 23 molecules. So this is the difference when it is in atomic state, when it is in molecular state. We have S for sulfur. Atomic weight is equal to 32 AMU. We shall write 1 mole of sulfur, atoms 32 grams and 6.02 10 raised to the power 23 sulfur atoms. But S8, a molecule of sulfur, not atomic weight, its molecular weight 32 multiplied by 8, 256 AMU. So, a mole of S8, 256 grams and equivalent to Avogadro's number of S8 molecules. This is in continuation with what we discussed yesterday. Before we attempt numerical problems on mole concept, we shall make one thing very clear. Whatever we are to find out or calculate, it will be converted into moles. Some weight is given, we shall convert it into moles. Number of molecules is given, number of atoms is given, it will be converted into number of moles. Very simple relations or very simple mathematical expressions. Let us try. Say a simple example. We are to calculate the number of moles in 100 grams of water. To calculate the number of moles in 100 grams of water. Molecular weight of water is equal to 18 AMU. We shall write 1 mole of water, it is 18 grams and 6.02 10 raised to the power 23 water molecules. This is the relation we shall write. Now, we shall solve it by unitary method and then try to formulate the relation between weight and molecular weight. Weight is given, weight of water, it is given, it is 100 grams and its molecular weight is 18 grams. So, what unitary method says, no cramming at all, no cramming at all, bilkul nahi. 18 grams of water means 1 mole, but weight is given 100 grams of water is equal to 100 over 18, it is 5.55 moles. We have solved this question, but we shall generalize these calculations. And how we shall generalize? In this calculation, what's in the numerator? Given weight of water 100 grams, we have divided it by molecular weight. So we shall write to calculate number of moles. Formula is weight of the substance over its molecular weight. We are to learn it, not cram it. And we have derived it. We are not cramming it, not taking it for the granted. We have solved this question. How could we reach this answer 5.55? What weight of what was given? 100 grams. Divided by its molecular weight, 18. The answer was 5.55. From this expression, how to calculate? Given weight of the substance divided by its molecular weight. This is the generalized picture of these calculations, and we shall learn it, we shall not cram it. We have another example, and that example is calculate the number of moles in a billion, in say 10 billion molecules, 10 billion molecules of carbon dioxide, 10 billion molecules of carbon dioxide. The given substance is carbon dioxide. It is a compound because it contains atoms of 2 elements, carbon and oxygen, maybe more, maybe single. We shall discuss examples. Molecular weight, it is 44 AMU. So 1 mole of carbon dioxide, 44 grams, same as this number of molecules. We shall use again a novel method. What we have to calculate number of moles. Among these three, which expression involves moles? This is mole. We are to find it. Put a sign of interrogation over it. This we have to calculate, and in the unitary method, what we have to found is always on the right hand side. From this number of molecules, among the two, where we have find molecules, here we shall take this point. Unitary method says this number of molecules means 1 mole, and what about 10 billion? We will get the answer. Define 10 billion. What is a billion, 10 raised to the power 9. 1 lakh, 10 raised to the power 5. 1 million, 10 raised to the power 6. 1 billion, 1000 millions are 1 billion, 1000 millions. So 1000 into 10 raised to the power 6, and it is 10 raised to the power 9. 10 billion means this, so this is 10 raised to the power 10. We are to convert this number of molecules into moles. How to start? 6.02 10 raised to the power 23 molecules of, we may write or not, carbon dioxide. It is 1 mole, and 10 raised to the power 10 molecules. This is the numerator. 6.02 10 raised to the power 10. This is the denominator, 10 raised to the power 23. This division will give us the answer. So it would be directly, we may put it like this: 1 into 10 raised to the power 10, denominator 6.02 into 10 raised to the power 23. Divide this, it is 0.166. Bring it to the numerator, 10 raised to the power 23. This minus 23 to be multiplied by 10 raised to the power 10 into 10 raised to the power 10. So it becomes 0.166, 10 raised to the power minus 13. This answer is complete. But generally, rationalized answers involve this figure where decimal comes after the first figure. What to do? It is 1.66. Decimal has moved 1 spot right hand side. This power will decrease. 10 raised to the power decrease from minus 13, it becomes minus 14. This is given answer, and to say this has been the rationalized answer looks smart. 0.166 doesn't look smart. This looks smart. Adjusting the values of exponential powers of 10, and we have number of moles of carbon dioxide in 10 billion molecules is 1.66 into 10 raised to the power minus 14. This is the simple calculation. Again, putting it into words, how we have calculated the number of moles. What was in the numerator? Given number of molecules. Given number of molecules, and in the denominator it is Avogadro's number. It is the Avogadro's number. Let's write it complete. So this is how we have calculated or derived it. We have to learn this, not cramming. Why not cramming? We have calculated, we have derived it. I didn't say the number of moles is equal to given number of moles as it is 10 billion divided by Avogadro's number. No, we have derived it. So there should be no problem. Just derive it once, second time, and you will get it. Just let us try to correlate what we have done up till now. And that correlation is number of moles is equal to maybe weight of the substance over its atomic weight or molecular weight, whatsoever is relevant. Number of atoms or molecules divided by Avogadro's number divided by Avogadro's number. These relations, two relations are directly related to the number of moles. We shall remember this relation whenever we attempt a question on mole concept. Whenever we attempt a question on mole concept, we shall convert what we are to found in number of moles. That question will be done in one step. There will not be any other step of calculations. I guarantee it. Have an example. Have another example. Calculate the number of moles in a kilogram of magnesium sulfate. Calculate the number of moles in kilograms of magnesium sulfate. पहला काम, molecular weight of magnesium sulfate. Magnesium 24, sulfur 32, oxygen 16 into 4, 96. 64. It is 120 AMU. This is the molecular weight. Given weight of magnesium sulfate in the statement kilogram, not allowed, it is 1000 grams. Therefore, number of moles, weight of MgSO4 divide molecular weight of magnesium sulfate, it is 1000 over 120. It is 8.33. This should be the answer to this question. 1 kilogram of magnesium sulfate is the same as or equal to 8.33 moles of magnesium sulfate. We move on to the next step. Different substances have different molecular weights. Molecular weight of magnesium sulfate is different from molecular weight of sodium sulfate, different from molecular weight of potassium sulfate, different from molecular weight of copper sulfate. So, when we select first option, same weights of different substances, since their molecular weights are different, their number of moles will also be different. Number of moles are different, so their number of molecules will also be different. Exception is when we have different substances with the same molecular weight, that is with the same molecular formula. We shall put all these examples on board where molecular weights are different, where molecular weights are identical. We have a molecular formula C6H12O6. We have a molecular formula C6H12O6. We don't know it. Molecular weight is 12 into 6 plus 12 plus 16 into 6, 72 plus 12 plus 96, it is 180 AMU. We are given C6H12O6 a formula. According to the formula, we have calculated the molecular weight, but this formula does not represent one compound. It represents glucose, it represents fructose, it represents mannose, it represents galactose, and many more. All these substances and many more have same molecular weight. If we take equal number of grams of these substances, since molecular weight is same, these will have same number of moles. Relation क्या है? Number of moles is equal to weight over molecular weight. Weight is same, molecular weight is same, number of moles will be same. But when the different substances have different molecular formula, their molecular weights will be different, and if we take same weight of all substances, they will have different number of moles and hence different number of molecules. Let us put it into a picture. Given that 18 grams of glucose, fructose, mannose are given, calculate the number of moles of each. C6H12O6, we have done molecular weight is 180 AMU. If number of moles is equal to weight over molecular weight. Weight is 18 grams over molecular weight is 180, 0.1. Each substance has 0.1 mole. And how many number of molecules? Avogadro's number multiplied by this number of moles and we get the number of molecules. Each substance has 0.1 mole of it and the number of molecules is equal to number of moles into Avogadro's number 0.1, 6.02, 10 raised to the power 23, 6.02, 10 raised to the power 22. This is the answer. This amount of glucose has this number of molecules. This amount of fructose has this number of molecules. This amount of mannose has this number of molecules, identical. Let us discuss when it is not identical. We have given that 10 grams of 10 grams of sodium sulfate, potassium nitrate, calcium carbonate. Calculate the number of moles and molecules of each. Calculate the number of moles and molecules of each. Na2SO4 molecular weight is sodium 23 into 2 plus sulfur 32, oxygen 16 into 4, 46, 32, 64, and this is 142 AMU. Number of moles, weight over molecular weight, 10 divided 142, we shall get the answer 0.7 something is equal to 0.7 something. Its answer, we have potassium nitrate, its molecular weight is equal to 30 plus 14 plus 16 into 3, 39, 14 and 48. I think 101 AMU, I suppose. तो फिर number of moles is equal to weight 10 over 101. It shall be 0.1 approximate. It will be similarly we have calcium carbonate. I think it will be 0.07. It will be approximate 0.1, and let us find that its molecular weight. Calcium 40, 12 and 4800 AMU. Its number of moles, weight over molecular weight, 10 over 100, it is exactly 0.1. Weight is same, number of moles are different, and in this second stage we shall find out the number of molecules. Number of moles are different, it is nearly 0.1, it is same as 0.1 and it is 0.07 because these substances have different molecular weights. In the earlier case C6H12O6, three substances, molecular weight was same, number of moles was same, and definitely number of molecules was same. In this case, weight is same, but molecular weights are different, so number of moles are different. We may go for the number of molecules also, because it was in the statement, number of molecules of sodium sulfate, number of moles into Avogadro's number, 0.07 into 6.02 into 10 raised to the power 23. We shall explain this relation also. We shall explain number of molecules of second compound was potassium nitrate, 0.01 into 1023 into 6.02, maybe approximately 6.02 into 10 raised to the power 21. And last of all, we have number of molecules of calcium carbonate, 0.1, and this is 22, 0.1, 6.02, 10 is for 23, 6.02 into 10 raised to the power. These are approximately same, not exactly, because number of moles was approximately same. This is how we calculate the number of moles, number of molecules. Everything depend upon the values of their molecular weights. For same amount of different substances, if molecular weights are different, number of moles will be different, number of molecules will also be different. How to create multiple choice question from it?